Okay, so next thing after this example, on page 354, we are going to talk about power. And power is nothing new. We've discussed this earlier with the translational motion. Now we're going to see how we're going to apply it to the rotational motion. Okay, I'm going to get my pen. So we need to kind of remember what the definition of power was. It is the rate of change in energy, right? And it is defined as the work, the change in work over time. Okay, so dW over dt. So this W is the work term. We have seen a couple different W's, and this is the work. And as we just discussed, the work term can be written in terms of torque times the displacement. Since this is a very small displacement, it's going to give us very small work, right? And so what we have is then power is defined as dW over dt, the change in work with time, and that's equal to, using this work term at the top, so we have tau d theta divided by dt. Now thinking about what this d theta over dt is, and writing the power in terms of that, and since this is the change in position over time, and it gives us an instantaneous angular velocity, right? So power is tau times omega, and that's for the angular or rotational problems. This is very similar to what we got for the translational case. It was simply force times velocity, right? In mapping, you can figure this out easily. Force goes to torque, linear velocity goes to omega. And both of them considers that these two are constant. So we have here that force and the torque are constant. Okay, so that's what then you can use torque times angular velocity to get the power, or force times linear velocity to get the power. Okay, and this is an alternative method. You can check that. I'm gonna skip it. So in the next thing is the activity. In the first question, I'm not gonna ask it as a clicker question, but I want to go over it with you. So here we have a motor, and it is used to spin a DVD disc from rest. So you can see the disc here. Couple things, let's highlight them. It starts from rest. A motor applies a constant torque to the disc. As the disc spins up to speed, the power provided by the motor, is it gonna stay the same, increase, decrease, or we don't have enough information to figure it out? Okay, I got rid of the options because it showed the answer. Let's figure this out. So what is power? Since torque is constant, now power equation, I can use torque times omega. Okay, I'm trying to draw omega and W differently. Sometimes they look the same. But this is the angular velocity, omega. Okay, so this is the power, and I just need to figure out how it changes. So what do I have? I know that the torque is the same, it's constant, so this doesn't change. So whatever happens to omega will happen to power. Okay, if I read the problem carefully, I already know what happens to omega, right? It starts from rest and it's going to spin up to a speed, so it's increasing. That would mean power should be increasing. Okay, so that's one way to find, but I want you to see it another way. If they didn't tell us the last sentence, and they didn't really need to do so, using the second law, sum of torque equals to moment of inertia times the acceleration, we can figure it out. Okay, we know that the torque is constant, moment of inertia is also constant, not changing. That would mean angular acceleration is constant as well, right? Nothing changes here. But what does that angular acceleration constant mean? And it is non-zero because you have a torque. It's constant, it's non-zero torque, and that would mean alpha is not zero, right? But it's constant. So how does this reflect on omega? What is omega, right? Since alpha is defined as d omega over dt, so that's the change in omega, is the acceleration, right? Angular acceleration. If this is constant, that means omega is changing at a constant rate. So it is increasing, and that's really all we need right now, but it's increasing at a constant rate. So the power is also going to increase at a constant rate. That kind of gives you a little bit more information because you know that change of omega is constant, and that's gonna also be related to the change in power, or and change in power with time, right? Okay. So so the answer for that is increase then. And the next of the activity is kind of giving you a little bit of like some questions, some calculations. I think this is really nice to go over. I would try to do it from the workbook, your own workbook first, and try to kind of figure the answers to the questions. And then there's some numbers given, so you can also see it mathematically, how it works out. I'm going to skip it though, because I want to focus more on the problem solving. And next thing is 2913. This is going to be a clicker question, and there will be like 5 of them from the same question because there's 5 different things that we are checking. So what we have is now we have the pulley and the hanging mass, but we are also adding a ring to the pulley. So how the things will change. So you're going to take a look at that and then answer questions. And the next part, again, I'm going to skip this part too. There's some numbers. You can check the answers, so you can kind of do a quick practice with them if you like. But again, we are doing those in the problem, so I'm going to skip these as well. But conceptually, it's really good problem, so I'm asking you to do the clickers. They're not optional, okay? They're on Canvas. And I'm going to make this one, 29.23, in another 5 problems. So this is going to be 5 clicker questions. Instead of a ring here, we have a solid disk, and you'll see how things changes, and you can compare with the ring as well. So it's a good practice. Okay, so this is a sub-part summary, and for rotational systems, the power is the torque times angular velocity. Okay, so we learned about that. P is equal to torque times angular velocity instead of F times V for the linear systems. And rotating systems can store energy as rotational kinetic energy, which depends on the angular velocity of the object and its moment of inertia. So we showed this with a subscript R, and this is 1/2 I omega square, right? I is the inertia, moment of inertia, and omega is the angular velocity. And we derived this equation from the linear kinetic energy, so we did that a couple of classes before, so if you don't remember, you can check that, because we are really finishing up the chapter, and I want you to really understand the concepts before solving more problems. Okay, those are the 2 we had so far. And the next one is conservation of energy. Still holds as long as we account for both translational and rotational kinetic energy. So we needed to split the kinetic into 2 parts, right? And that's the last modification we will do in this class. Again, in future classes, you may need to add more stuff. And for as an example, we are going to talk about electrostatic potential. So we are going to have another potential term in that equation. So there are different types will be added in different classes as well, okay? And the moment of inertia plays a significant role in rotating systems. So it's not just the mass, it is really the distribution of mass. So where the mass is located matters when the objects are rotating. And and how we kind of show that in the equations are in terms of moment of inertia, I. And so be careful with this. I is going to be mr squared if it is a point mass, but if it is not, you have to use table 10.2, and that is going to be given in the exam, especially as a handout, like as a separate just like equation sheet. This is going to be given to you, so you don't need to memorize anything, but you need to really understand how to use it and if you need to use also parallel axis theorem or not, as we just did in the previous problem. It was a very complicated problem. So make sure those problems are crystal clear. If you have any questions, please don't hesitate to ask questions during the Zoom meetings. Just make sure to get help. Okay, in the next video, I'm going to solve example 39 on the page 358.